Hello everyone. Today I'm going to present to you the brief synopsis of what we are doing in the AHEAD project. AHEAD stands for Advanced Hybrid Engines for Aircraft Development. This is a European Commission sponsored project under the FP7, Framework Program 7, and it started in October 2011 with a duration of 3 years. Now what is the project about? Now if you look at aviation on an average, and aviation is a great contributor to the society. It brings people and cultures together and creates economic development across the globe. Air routes are the highways of world economy. Civil aviation has progressed a lot since the inception of Comet, the first aircraft, the first jetliner, which came in the late 50s and the early 60s. Over this period, the fuel consumption per passenger kilometer has reduced by around 75%. And that's a huge reduction. And a large part of this reduction has actually come from engines, which contribute to the major part of this fuel reduction. Now, the rest of the reduction in fuel consumption came because of improvement in materials, aerodynamics, avionics, etc. That's what you can see here in these graphs. Now, if you look at other things which contributed to this fuel efficiency, then also a significant contributor to this fuel reduction was the fact that we have managed to put more people in a given space. And that's why earlier flying was a pleasure and today it is not. Now gone are the days when air travel used to be a pleasure, at least in the economic class. That's true. Now, on the other hand, the air traffic increased several folds over this period. As can be seen in the chart, the air traffic has increased on an average 5% per year. Now there have been moments of hiccups like after 9/11 attacks and so on and so forth, where there was a bit down, the industry was a bit down, but however, overall growth in the aviation industry has been quite strong and steady. In the past 10 years, passenger numbers have grown by 45%. The freight traffic has increased by more than 80% on a ton-kilometer basis. Along with these positive developments, some serious challenges for aircraft emissions and community noise and the availability of fuel resources are encountered by aviation. Now, these are some of the challenges that we need to overcome. The increase in CO2 emission by aviation can be seen in this chart, which is shown. And we know that CO2 emission contributes a lot to global warming. If aviation has to sustain a growth in the future, then the main challenges faced by aviation is shown in this chart. First of all, efficiency. We have to increase the efficiency of our aircraft, our engines, our operations, and even further, we have to reduce the harmful emissions. The emissions from the engine near the airport, and not only near the airport, but also for the entire mission. Now, most of the aircraft have already expanded to their maximum passenger handling capacity. Noise restrictions near the airport is one of the main bottlenecks in increasing the airport capacity today. So we have to reduce noise of our aircraft and engines as far as possible. Right from the beginning of aviation, aircraft have been using jet fuel as their primary energy source. However, as petroleum resources are getting scarce, we have to look for other resources. And that's why energy source is going to be a major challenge for aviation. To take this further, many of these challenges explained earlier in the slide was summarized in the ACARE vision document called as Flight Path 2050. ACARE stands for Advisory Council for Aviation Research and Innovation in Europe. It's a body which formulates the high-level vision for European aviation. Now, some of the goals has been shown in this chart. The perceived noise levels should be reduced by around 50% by year 2050 as compared to an aircraft, a baseline aircraft in year 2000. The CO2 and NOx emissions should be reduced by around 75% and 90% respectively as compared to the year 2000. Now, if you look at these challenges, they are very, very ambitious. Achieving these goals calls for a revolution in aviation technologies on all fronts. The aircraft, the propulsion system, the integration. Apart from the challenges mentioned in the earlier slide, the energy source still remains a major challenge for aviation. Now, the figure on the left shows the demand of jet fuel in million liters per day. Today, we are using more than 1 billion liters of jet fuel every day for civil aviation, and this is enormous. On the other hand, the production of crude oil is shown on the right chart, and according to the Hubbard's peak theory, presently we are close to the peak of oil production. In fact, we have surpassed that peak, and very soon we will reach a stage where the supply cannot meet the demand anymore, thus increasing the fuel prices like anything. Now, this would be a nightmare scenario for aviation and everyone else, and flying would become too expensive for the people, and it would become a privilege for very few people in the future if we don't do anything. So the main question is, how can we continue to fly when there would be no more petroleum available? Now, some people say that we could use biofuels. There is no way that we can produce such a huge quantity of biofuels available all over the world in a sustainable manner without affecting the food chain or the environment in a harmful way. Now, one of the possible evolutions of energy source for long-range aircraft is shown in this chart on the right-hand side. It's really difficult to predict how things will go, but this is an anticipation. And what we anticipate is that we will continue to use jet fuels in the coming decades. The use of synthetic fuels and biofuels as drop-in fuels will increase. However, if we want to reduce CO2 emission and if we want to be more sustainable, then we have to move towards cryogenic fuels like LNG, liquefied natural gas, or liquid hydrogen in the later part of the century. This chart shows various fuels that can be used as energy source for flying for an aircraft. Now, if you look at the x-axis, it shows the mass energy density of these fuels, which indicate the amount of energy that can be carried in an energy source per unit mass of energy source. So basically, how many megajoules of energy I could carry per unit weight of the energy source. On the y-axis, what you see is the volumetric energy density, which means it indicates the amount of energy that can be stored in a unit volume of the energy source. Now, if you look at kerosene, for example, what you can see is kerosene has quite a good energy density and also quite a good volumetric energy density. Well, the dream fuel for aviation would lie somewhere on the right corner of this chart, which unfortunately doesn't exist. Electric batteries have very poor energy density, and therefore we cannot use electric batteries as energy source. Now, what you also see is liquid hydrogen, for example, is very good in terms of energy density, but is not good in terms of volumetric energy density. And LNG is somewhere in between kerosene and liquid hydrogen. LNG is also one of the cleanest fuel at the moment. It is also widely available. Looking separately at the CO2 emissions, again from a well-to-wheel perspective, one sees that gasoline accounts for about 30% more emissions than LNG. One can also view that overall CO2 emissions for LNG is the smallest compared to the whole range of type of fuels. Now also, using LNG as a fuel reduces the resulting NOx and particulate emissions, because LNG is quite LNG is quite a clean fuel. In addition to the fact that LNG already is one of the most environmental friendly fuels existing, there's a lot of potential across the whole LNG chain for further reducing the greenhouse gas emissions. However, carrying cryogenic fuel in a conventional aircraft is a problem. Normally, the fuel is stored in the wings of an aircraft. However, cryogenic fuel should be stored in well-insulated cylindrical tanks. Now, these tanks cannot be stored in an aircraft and have to be stored within the fuselage, because normally the fuel in an aircraft is stored in the wings. As shown in this figure, you can see that the cylindrical tanks were stored within the fuselage. This is from the cryoplane project that was sponsored by the European Commission. However, storing tanks within the fuselage increases the fuselage volume substantially. It increases fuselage drag, and this increase in drag increases the required thrust and hence the fuel consumption. And you can see that conventional aircraft configuration is not suited for storing cryogenic fuels.
A little louder, the volume.
Okay.
Yeah.
Now, we came with a novel solution for storing cryogenic fuels. We are using a blended wing body aircraft. The extra volume within the blended wing body aircraft can be used to store cryogenic fuel tanks without incurring much drag penalty. We also optimized the space utilization by storing some biofuels within the wings, as can be seen here. Now, this unique multi-fuel blended wing body aircraft configuration makes carrying cryogenic fuel on board the aircraft much easier and also safer. This unique novel configuration has the potential to change the aviation like anything. Now, this could be the most significant step change in aviation after the introduction of Boeing 747. Now, based on this novel idea of a multi-fuel blended wing body, the AHEAD project and its consortium was formed with the aim of investigating the feasibility of this novel aircraft, the multi-fuel blended wing body, and to design an engine for this unique aircraft. Now, AHEAD stands for Advanced Hybrid Engine for Aircraft Development. The consortium consists of Delft University of Technology, with me as the technical coordinator, WSK Reszów, an aero engine manufacturer from Poland, who is the main industrial partner in the project, the Technical University of Berlin, which is primarily investigating the hydrogen combustion chamber, as I'll explain it later on, DLR Institute of Atmospheric Physics in Oberpfaffenhofen, looking at the effect of cryogenic fuel on atmosphere and climate change. Technion from Israel is looking into flame-based combustion chamber, and Atkunta is taking care of project dissemination. The project started in October 2011. Now, this special multi-fuel blended wing body that I mentioned to you will require a special type of propulsion system. Now, what is shown on the slide is a schematic of a new type of engine for this aircraft. It's called as hybrid engine. Why hybrid? Because it uses two different fuel sources, one cryogenic fuel and second biofuel. Now, because this uses two different kinds of fuel, it has to have two different kinds of combustion chambers. Now, the first combustion chamber, which is located between the high pressure compressor and the high pressure turbine, is the combustion chamber that uses hydrogen. Okay? Now, this is the typical what is used in a gas turbine, in a conventional gas turbine as well. The second combustion chamber is located between the high pressure turbine and the low pressure turbine, and it is called as the interturbine flame-based combustion. Now, this combustion chamber uses biofuels for producing energy. Hence, the gases entering the second, gases entering the second combustion chamber are very hot and have reduced oxygen concentration, it is possible for the second combustion chamber to use a unique kind of combustion technology called as flame-based combustion. The two combustion chambers are placed such that they reduce CO2 emission and NOx emission and soot emissions at the same time. Now, apart from the combustion chambers, the engine also has several other novel features. Normally, all engines, a significant amount of compressed air is used for cooling turbine blades. Now, this is due to the fact that turbine blades are normally operating much beyond their melting point temperature. Now, this cooling air is normally extracted from the last stages of the compressor. Actually, this cooling air is not cold. Typically, it's around 600 degrees or more. But it still can be used to cool turbine blades. However, extracting this air from the last stages of the high pressure compressor reduces the engine efficiency quite a lot. Now, in this unique hybrid engine, we are using cryogenic fuel to cool the air that is extracted from the last stages of the compressor. Thus, we cool the air that is used for cooling the turbine. In this way, we reduce the amount of the air that is required for cooling drastically. Now, this increases the efficiency of the engine even further. The engine also features a counter-rotating fan, especially designed for integrating the engine and the aircraft in a synergistic manner by using what is called as boundary layer ingestion. The AHEAD project is divided in 4 work packages, and this chart gives you an overview of various technologies that are being investigated in the project. What we can see is right from the beginning, the whole entire engine is being designed with environmental considerations, and the final work package is basically defined in such a way that the environmental assessment and integration can take place in a synergistic manner. Now, I would like to describe you briefly the work done in various technologies that I described earlier. To start with, the multi-fuel blended wing body. The main design drivers for the aircraft is shown in the slide. It's a multi-fuel. That means it carries 2 types of energy sources, one cryogenic and one liquid fuel. The cryogenic fuel could be either LNG or liquid hydrogen. and the liquid fuel could be kerosene or biofuel. Now, of course, the main goal of the aircraft was to meet the cargo goals. It is designed to carry 300 passengers with a range of around 14,000 kilometers. So it's a long-range aircraft, because this is a market that we see is going to grow quite a lot. So point-to-point connection. You can fly directly from Amsterdam to Shanghai, Beijing, Tokyo, Osaka, and all other places. And it should be available for 2050. Now, the aircraft is designed, as I said, for two different kinds of fuels. Now, right from the beginning, the aircraft is being designed with the aim of reducing emissions and pollutants. Conventionally, an aircraft is designed with an objective of reducing fuel consumption, and later the impact of the aircraft on the environment is evaluated. Now, this is the first aircraft in which environmental considerations are being taken into account right from the beginning in the design. The aircraft, as I mentioned, is a long-range aircraft. Now, one of the important points which policymakers in aviation have totally missed is the fact that we as humans are evolving faster than ever before. In the past couple of decades, the average weight of passengers has increased more than 10 kgs. You can see in this slide. Now, this increase is quite significant. Thus, the average passenger weight that was assumed during the design of Boeing 747 in the 60s is not valid anymore. We have taken this into account in our design phase. Now, some of the salient features of this new aircraft design are listed in the slide. Apart from using multiple fuels, we use the new and unique hybrid engines in this aircraft. We integrate engine in the aircraft in a very unique way called as boundary layer ingestion. Now, this is a challenging way of integrating the engine and the aircraft. However, there are certain benefits that can be harnessed from such an integration. We are looking into this. The noise can be reduced significantly, and also the fuel consumption can be reduced a bit. By the year 2050, active flow control technologies will be available, which could be used to increase the laminarity of the wings. What we are also using is canard for the aircraft, because blended wing bodies normally have a nose down tendency. Now, we have looked into several configurations, like for example here, how we can place the passengers, how we can segregate the space between the passengers and the space for carrying cryogenic fuels. We have looked at different fuels, as I said, LNG as well as liquid hydrogen. Now, this is a concept Bravo, which had a different way of configuration of aircraft. One of the main considerations that was looked at was the evacuation rule of 90 seconds. A lot of trade-off was done. This is one more configuration that we looked into. Again, every configuration has slightly different features, slightly different configuration in terms of how we separate passenger section and how we store fuels and what kind of fuels do we use. Of course, what we chose was Charlie, the third concept that you see on the slide. Preliminary design procedures were used. So we went from conceptual platform to preliminary sizing arrangement. And then we estimate weight and CG. After that, we looked at stability and control, aerodynamics, structures, performance analysis, and this loop was carried on over and over till we could converge to a reasonable design. After going through various stages of the preliminary design process, the multi-fuel blended wing body is shown on this slide. It uses canards for stabilization. The two engines are mounted at the rear of the aircraft and are partially buried, such that most of the fan noise can be deflected upwards and not downwards to the population staying around the airport. The cryogenic fuel is stored in fuel tanks, which are located at the rear of the aircraft and partially under the belly in the luggage compartment. This is a schematic of the engine as it looks today, but this is a work in progress and it's changing. Now let's look into some of the technologies that are going inside. Now, this is the new burner configuration designed for hydrogen combustion. Now, hydrogen is a reactive fuel. Hydrogen also leads to higher flame temperatures, which increases the NOx formation. Now, this poses several problems in terms of combustion chamber design. Thus, designing a low NOx hydrogen combustion chamber is a huge challenge for designers. Now, within the HUD project, the Technical University of Berlin managed to design a burner which can be used as a basis for designing hydrogen combustion chamber. Now, this burner uses a combination of swirl and axial injection to allow for pre-mixing of the fuel without facing the danger of flashback. Now, what do I mean by flashback? It's a phenomena what happens when hydrogen flame starts creeping up towards the fuel injector, because hydrogen is so reactive. Now, this can be catastrophic, and it can burn down the whole combustion system within a few seconds. The pressure losses within this new combustor design is also within the acceptable limits. This new burner was tested in the combustion test rig of Technical University of Berlin. Diagnostics instruments were used to characterize the burner and the combustion zone. The new burner design was tested at atmospheric pressure. This is the schematic of the burner. The burner was tested at various inlet temperatures and equivalence ratio, so various air to fuel ratios. And within this range of equivalence ratio, that is likely to be encountered in an engine operation, the burner exhibited very stable operation without any flashback over a long period of time. So that has been one of the major achievements of the AHEAD project. As I've explained earlier, we use two different kinds of fuels, and that's why we require two different kinds of combustion chambers. The second combustion chamber, which uses biofuel, is actually situated between the high pressure turbine and the low pressure turbine. And it uses a very unique combustion technology that we call as flameless combustion. And what is flameless combustion? Flameless combustion is actually a kind of combustion that takes place at high temperatures and low oxygen concentrations. And what is the unique feature of this technology is that the NOx emissions from this combustion is very, very less. And we want to use this technology in the second combustion chamber so that the NOx emissions from the AHEAD engine are very less. Now, this is the second combustion chamber, and you see that it looks like a bubble, actually, and this is designed to create a large amount of recirculation within the combustion chamber. This recirculation in the combustion chamber enhances the temperature and reduces the oxygen concentration. This is what we require for flameless combustion. The combustion chamber is very unique design. The prototype will be tested at atmospheric conditions in IST Portugal. The Technion from Israel is actually spearheading our efforts in terms of designing this flameless combustion chamber, and we are trying various configurations. We are eagerly waiting for the results from this test, actually, because this will be really a revolution in terms of combustion chamber design as far as gas turbines are concerned. Our partners, WSK, the industrial partner, is involved in designing a cryogenic heat exchanger for cooling the bleed air. And why do we cool the bleed air? Because this technique of cooling the bleed air enhances the efficiency of the engine. It also has another advantage, and that the fuel going in the combustion chamber becomes heated. And when it gets heated, the amount of fuel required in the combustion chamber also reduces. So we have two advantages of using a heat exchanger to cool the bleed air. We use the onboard fuel in a synergistic manner to increase the efficiency. And we have performed the sizing of various components in this heat exchanger, and the design has some unique features, and that's why it's under patent at the moment. In terms of engine performance, when compared to the baseline engine of G90, which is used in the Boeing 777 aircraft, and that is the baseline aircraft for our whole design, we see that the hybrid engines can reduce the energy consumption and CO2 emission per unit thrust produced while increasing the specific thrust. Now, for the LNG version, the CO2 emission from the hybrid engine is around 28% less, and when compared to G90, it's around 90% less. Now, this is a significant reduction. However, this reduction is only from the engines. When we club this reduction from the aircraft as well, because we also use a blended wing body aircraft, which is aerodynamically much more efficient, then the results can be seen in the next slide. And what do we get? When we compare our aircraft with the baseline aircraft, that is Boeing 777-200, then we see that the CO2 emission is reduced by around 65% when we use LNG and biofuel as our energy sources. And this reduction is based per unit payload, per unit kilometer basis. Now, the reduction in CO2 can be increased further by using liquid hydrogen and biofuels. However, since the life cycle carbon footprint of hydrogen is not well known at this moment, so the exact numbers cannot be predicted. The particulate emission is also significantly reduced due to the cryogenic fuel and flameless combustion especially. And since the blended wing body has more volume per passenger, we believe that it would give a more comfortable travel for people. Now, the multi-fuel blended wing body with hybrid engines, they reduce the emission of CO2 significantly. However, there is a penalty, and the penalty is the increase in the water vapor content because we use cryogenic fuels. Now, even the water vapor is less harmful in terms of global warming at lower altitudes, but at flight altitudes, the effect can be significant. Now, what we are doing with DLR is that we are looking into the effect of this increased water vapor content on the global warming. Now, this is a very complex phenomenon, and there is a serious lack of understanding of how this phenomena occurs in general. And our partner from DLR, the Institute of Atmospheric Physics in Oberpfaffenhofen, are tracking this problem. They are looking into the effect of increased water vapor content, the reduction in soot emission, etc., on contrail formation, and how this contrail formation actually affects the greenhouse gases in general, or the greenhouse effect in general. Now, preliminary studies show that if we fly higher, the increased water vapor content will increase the greenhouse effect. However, we are working on optimizing the flight mission with respect to the greenhouse emissions. And at the moment, we don't know the optimized mission, but in the due course of time, we will come to know that. Now, I showed in the earlier slide what are the main challenges of civil aviation. And I'm proud to say that the AHEAD project tackles most of these challenges. Just to summarize the main achievements of AHEAD, we gave a new configuration to the aircraft, the multi-fuel blended wing body aircraft, and this configuration has major advantages as compared to the conventional tube and wing aircraft, especially for long range. The novel way in which we are trying to store cryogenic fuel tanks in the aircraft can overcome some of the inherent disadvantages of blended wing body. Thus, we increase the feasibility of the blended wing body aircraft. We give more credible options for future energy sources. So not only looking at long-term options like liquid hydrogen, but also short-term options like LNG, which is very cheap and quite efficient. We have designed a new low-NOx combustion system for hydrogen as well. And this combustion system is not prone to flashbacks, and that is very important. Now, we are designing the first interturbine flameless combustion chamber, and if proved successful, then this will be really a step change in terms of combustion technology that has been applied to aero engines. And of course, we are also working on the bleed cooling concept. Now, in the end, I would like to pay the tribute Dr. Zbigniew Grabowski. He was a member of the AHEAD advisory board. Unfortunately, he passed away in January 2013. We will always be indebted to his guidance and support during this project. The AHEAD consortium is shown in the slide. You can see that Delft University of Technology is the coordinator. Our industrial partners are WSK. The Technical University of Berlin is participating, especially with respect to the hydrogen combustion chamber. DLR, Institute of Atmospheric Physics, is looking into the effects of the aircraft on the atmosphere. Technion, Israel Institute of Technology from Israel, is looking into the flameless combustion chamber. Adkunta is taking care of the dissemination activities. This slide shows the advisory board members of the AHEAD project. It's basically MTU Aero Engines from Germany, EASA, KLM, and EADS Innovation Works. Thank you.